class today. I want to give an introduction to algebraic geometry in algebraic group, so I hope it will not be too boring for those of you who know the subject, but I guess I cannot continue without having this. So in this talk, we fix a field K, which is algebraically closed, and actually this should be enough. But also in view of the thing that I want to do eventually analysis on varieties. So, or to consider measures on such, etc. So I want this K to be not the algebraic closure of Q, for example. C is much better than that. But C is not the only one, and having a complete separable absolute value. So actually it will not come about much in the talk, but this is what I want to think of. And maybe the only example we know is C for this, but there are others, so I just want to keep this in mind. For example, one can consider CP. Completion, so when I said complete, so complete means that the metric that the absolute value gives is complete. And whenever you have a field with an absolute value, you can complete it, and this is another field which is complete. And if your field was, to begin with, algebraically closed, then the completion is algebraically closed as well. And if you have any field with an absolute value, then there is a canonical way to extend this absolute value to every algebraic extension. And if you are familiar with QP, the periodic numbers, you can extend the absolute value on the periodic numbers to every algebraic extension of it. So also to QP bar, the algebraic closure of QP. And then you can complete, and this is what you get, CP, an algebraically closed field with canonical absolute value on it, which is extension of the periodic absolute value. So those fields are a good link between algebraic geometry and differential geometry, or whatever, usual topology of manifolds, and the completion of the algebraic closure of QP. And there are other fields, and actually, again, what I will do is consider the final algebraic geometry of an algebraically closed field, and this will not much come about in the discussion, but I do want to have it in mind, and I will make some remarks. And maybe I should mention another thing that I was considering while preparing these lectures is whether I want to do everything over algebraically closed field alone, or to consider the slightly more sophisticated version of algebraic geometry over non-algebraically closed field, which slightly complicate things, not too much, but somehow exactly because one wants to consider the real field or the periodic field. But if you are willing to deal with these guys, then this is not much of a difference eventually. Okay, and I assume that algebraic geometry is not completely a new field to anyone here, so everyone saw something somewhere. So I'm allowing myself to be brief with this introduction. For example, when I consider affine varieties, let me take this shortcut in defining it. This is the category which is, maybe this is the dual category of affine algebra. Okay, algebras. And by this I mean, there should be points here. Finally, generated K-algebra with no neighborhoods. So you're probably familiar with some basic affine algebraic geometry, and you have varieties, and the affine algebras are the spaces of functions, regular functions on varieties, but actually there is duality of category, and maybe for definition this is the best way to give a definition. So objects are affine algebra, so these are objects adjectives, and morphisms are just k-homomorphisms between such, only dualized, considered in the other way around. Let me, so if you do want, and of course we do, want to think about things geometrically, I want to think about the points of the space underlined, and this is what we call the spectrum. And let me to begin with define it as the following manner. So the maximal spectrum of A in affine algebra will be the space of all homomorphisms as k-algebras to this final object K itself. So this is a set. Now, here's a fact, I will explain this, but this is basically a notion that is that let's go to this. I can view the elements of A as functions from X to K. And the notion that says that this is an injection. And this is really what gets the theory goes, get it going, and I will explain this. And of course, we define this map by duality. So if A is in A, I define A at X to be actually X of A. A is a map from the guide A to B.
So what are assumptions about A?
Such. Find generated K-algebra with no difference. So it's the set X that I want to think of as the object of mine. Only I want to think of A as some extra structure on it. So this is just a twisted way to think of things, but this is what is very powerful. And though X with two topologies. The topologies, or the weakest topologies that make the functions of A, which think of them as functions, and I think I call them the regular functions. Continuous. So elements of A are functions from x to k, and on k I may form two topologies, and I may require all the functions from A to be continuous, and this gives me two topologies on x. The topologies on k, let's start with. Well, the confining topology this is the risk topology, if you wish. And I mean, this is if you want 0 to be a closed point, and also you want your topology to be shift invariant, the elements of k, then you have to have all points closed and take the minimal such topology. This is the risk topology on C, on K. So, and also you have the other topology and the absolute value topology. This is the standard topology on C, if you wish. Let's call this the Hausdorff topology. Get the Zariski topology and Hausdorff topology on X. Clearly, since points are closed for the Hausdorff topology, the Zariski topology is weaker than the Hausdorff for K and for every X. Z is weaker than H. So morphisms, of course, we have already defined what morphisms are, but in our dual point of view, these are maps x to y, fine. And of course, whenever you have a map from a set x to a set y, you can pull back functions by precomposition with this map phi. X and y are thought as, and those symbols represent spectrum. And phi star defines a map from regular functions on y to functions on x. And now, this is a requirement that when you pull back such function, it is still regular. So exercise. Check that phi star is both Z and H continuous. And this is by the fact that I'm using quick topologies now for definition. This should be very easy. Sorry?
Star is a homomorphism
This is a homomorphism function.
from algebra.
Yes.
In exercise, remove the star.
Здесь это получается,
Thank you. Okay. Now I try to I emphasize the injectivity here in my discussion. And let me go back to it. How to show that A injects into so there are two steps here. I want to discuss this. First, and also how to justify. Maybe I define. Probably you are familiar with the maximal spectrum of an algebra. This is the spectrum usually defined to be the spectrum of all maximal ideals in the algebra. While every maximal ideal, of course, gives me an homomorphism. Maximal ideals are in one-to-one correspondence with homomorphisms into fields. And here I said that these are the homomorphisms into the field K. So there is something special going on, and this something special is called, K and not anything else. This something special is called the Zariski lemma, or which is equivalent to the null results. And so let me describe this, because I will use this kind of thing in the near future. So why not actually discuss it in full? For A, think of it as a function. I want to sorry. I want to show that for any function there is some point little x such that a of x is not zero. The image of a non-zero element is not zero. So I'm constructing this. So pick a maximal ideal in A when I invert A. So this is take the algebra A and add localized or add the symbol 1 over A. Since there are no nilpotents, there is no problem with localizing in this way. You should think of it. A is not nilpotent, so I can the semigroup generated by A, all powers of A is, could be that doesn't include 0, and I can add this and in here and consider. So when every algebra has a maximal ideal in it, this follows its own name or something, and consider the map A to A over A. And this is a field. And actually I claim that this field is K. And why is that? We know that A, so we know that A is finite generated, also this guy is finite generated. I just added one more symbol, and now the image, the subjective image of finite generated is still finite generated. This is clear. And so we're going to apply the following to that algebra, that field. And this is the risky lemma. A and a fine algebra is a field if and only if A is K itself. I could write A equal, because K embeds also, probably I didn't say it, all algebras here with one, commutative with one. And K embeds canonically in A. And this canonical embedding should be all of A. And here's the remark. So coming from another field of mathematics. So we have spaces here and spaces of functions on them and some duality going on. This is familiar also from the theory of compact halves of spaces and 6-star algebras. right? So we have a very similar theorem, Gelfand theorem for C-star algebra, saying that a C-star algebra which is a field must be C itself. So this is, in some sense, an analog of that. Compare with Gelfand. A C-star field. Just for continuing, let me write down the remark that we made. The corollary of Zariski lemma is that the collection of M in A such that M is maximal is naturally isomorphic with all homomorphisms, K algebras, from A to K. Again, a priori, without Zariski lemma, this would be all homomorphism from A to fields. And those fields that you will get are K, always. So before proving Zariski lemma, let me prove this lemma, which is very much related, and I will use anyway in the future. So this is why I choose to, again, to present those things, even though this is very basic. And the lemma I'm presenting now is sometimes called in algebra going over, lying over. The geometrical meaning of it is that, and I will express this in the future, is that finite maps between varieties are always open. But this is complete algebraic lemma. Or maybe before the lemma thing, make a definition. So, A inside B is an integral extension this is injection of, could be of rings, but in our context of K algebras. Fine. I'm not trying to be as general as if B is a finite rank or finite generated as an A model. Whenever you inject A into B, you can think of B. B is an algebra by its own right, so just think of multiplication by elements of A. So B is an A module and A module to be finite generated. And dually, so think about those things in geometry, such maps are called finite morphisms. And the lemma is if A inside B is integral extension, an ideal in A, I'm not writing down, but this symbol. Then A is Gothic A is an ideal in capital A, the Latin A, then
Little a is just an ideal in capital A or not?
just an ideal,
An ideal.
any ideal. Okay. Then I can take the ideal generated by A in B. This is denoted A times B. Is the ideal generated by little a. Consider A as a subset of B. So consider little Gothic A as a subset of B and take the ideal generated. Maybe. So, if A is not everything, then the ideal generated by it is not everything in B. And the proof of it is some version of the Kayama lemma. I will give an explicit proof for it for you guys. So let's assume that AB is B and show that A must be A. Or that one is in right B as a direct sum of A times BI for some silent generating set. This is expressing dialect. Sum of BI is a finite generating set of B, and without loss of generality, I may assume that B1 is 1. This expression over here saying that each of the BI's I can express as finite combination of linear combinations of the other B's of all B's with elements in the ideal A. And this is express this as the following. In matrix notation, take B1 to Bn, and each of them could be expressed with AIJ's time same generator. The AIJ's here are in the ideal coefficients now. Is this clear? But then I get that just subtract B, that vector, and this gives, just take this expression, Aij minus delta ij times B, and everything is happening commutatively, so multiply here on the left with the adjoint of that, the adjoint matrix. And of course, this is just the determinant of Aij minus delta ij. This is a constant times the whole vector B. And eventually, I know that these two are the optimal. And now just read this at the first line of this matrix equation, well, B1, and recall that B1 is 1. So, this, again, the first line, what is going on, and this is determinant of that thing, times 1. That's this number, and now observe, if you open up this determinant, that all the terms in the determinant, the determinant is just sum of generalized diagonal monomials, and only one of them will not have all the elements in A. So this is, make this computation, or observe that this is in 1 plus A. Hence 1 is okay, any question? So I gave this very explicit thing, although very familiar probably, for 2 reasons. One is to prove the risky lemma, just for completeness, and the other is that I will use this in the near future. Okay. So again, the risky lemma is saying that every affine algebra, which is a field, is K itself. So I'm proving this. So I'm having this A, and it is finite generated. So I can write it down as K with some finitely many generators. Now I want to split it into 2 things. Take the generators, take a maximal subset of the generators, call them x, x1 to xn, which is algebraically independent, and the rest called y1, yn. So let me write it down. X is x1 to xn algebraically independent. Then over k. So if you just take kx, this is just the ring of polynomials. Y, you know, then y1, ym, algebraic over the rest. So each of the y's, y1 say, satisfies some polynomials with coefficients in here. This polynomial need not be monic a priori, but if I divide by some polynomial in kx, it will be monic. The coefficients of the, so it's y1 will satisfy a polynomial in kx and some other variable, t, I don't know, something else. And the coefficients of the polynomial in t will be polynomials in kx, and maybe to the highest power of t there will be some coefficient. Let's divide by this coefficient, and then y will satisfy a monic polynomial. And this means that the module generated by y will be finely generated, because some power of y will be expressed, this power of y, will be expressed as a combination of the others. So this means that y is integral, or generated an integral extension, maybe not over kx, but over kx when I'm allowing myself to divide by some specific polynomial, depending on this y1, similar for y2, etc. So take all these polynomials, multiply them together, allow yourself to localize by this one. So y, y1, yi's are integral over kx when I'm allowing myself to divide by for some f in kx. Oh, okay. constant. And A is an integral extension of this guy, Kx. But A was assumed to be a field. A has no trivial ideal in it. So the lemma we just proved, taking well, A to be B and this guy to be A in the presentation of the lemma, gives that actually this guy has no ideal, has no non-trivial ideal. Is a field. Well, as well as A. That's our assumption. The property of being a field goes down under finite extension, under integral extension. But this is an absurd. In Kx is just a ring of polynomials. You have many irreducible polynomials. Infinitely many irreducible polynomials. You can prove this the way you prove infinitude of primes. Same proof that works. So maybe now take if f if the f is really a polynomial here, not a constant. If then f plus 1 generally will be an ideal.
What are you proving now?
I'm explaining the proof of the Zariski lemma. I'm assuming that A is a field and I want to derive a contradiction. So I go that this is a field.
Yes.
And actually I want to explain this cannot be unless this thing is K itself. At this stage of the proof, I'm trying to prove that this is K. Well, I want to show that actually you don't have any variables here. A is K. I mean, maybe I should.
I see.
There are no x's in this. A priori, this is just an algebraic extension. And actually, yeah. Now, okay.
Yes.
What I want to show now is that A is an algebraic extension of K. There are no x's here. No algebraically independent parameters.
Why is this Kx of 1 over f a field?
So this should follow from the lemma. We know that A is a finite extension of this one, and we know that if you did have a non-trivial ideal here, it will extend to a non-trivial ideal here. This is what the lemma tells you. A field is exactly those creatures that don't have any non-trivial ideals in it. So since we do assume that A is a field, and we do know the lemma, we get that this is a field. Now what I'm trying to show is that there are no x's in this business. I guess my notation kind of assumes some finitely many, non-zero finitely many x's, so my notation is a bit bad, but this is what I'm trying to explain now. What I'm saying is that in Kx, you have many irreducible polynomials. When you construct the field of rational functions over K in the variables xi's, then it is not enough just to invert one element, 1 over f. It can't be that we arrive here in the field. I'm arguing by contradiction. Take f plus 1, the ideal generated by f plus 1. This is a non-trivial ideal. Unless, well, f is a constant. A non-trivial ideal in Kx. space.
By saying that your notation propagates.
Let me proceed. In case f is in k, kx1 over f is just kx, and this is not a field, of course. And x1 is a non-trivial ideal. Unless there are no x's. So here as well, my notation is bad. In my notation, I assume there are x's. Sorry for that. I was careless. A is just k with y's, and it is algebraic over k. But k was assumed to be algebraically closed, and this implies A. Okay, and I hope this is clear. And before taking a break, I want to conclude another geometric interpretation of that same lemma. I kind of mentioned briefly. So every finite morphism of algebraic varieties of finite algebraic varieties is onto. So again, by finite morphism we mean some y to x, I guess in my notation here, such that the corresponding a to b is integral extension. B is a finite module over a. And I wish I had the time to give more examples. I hope you are familiar with some. Maybe we can do it later.
But,
Yes.
but if you define integral extension as just a monomorphism, then this map from 1 to x, which is dual category, a map corresponding to a monomorphism is onto by
It is not onto by definition. Actually, I guess I failed to say it explicitly. I have too many things to say. It is dominant. What does follow on the level of points is that the image is dense, which is a property called in algebraic geometry dominance. So yes, in set theory, if you dualize maps on function spaces, x goes to y, set theoretical map, if and only if the map functions on y to functions on x is injective. In topology, I guess you need to use the topology. X goes to y for nice topological spaces. So the map from functions on y to functions on x is injective if and only if the map from x to y has a dense image for nice topological spaces. And same here. So what we don't know a priori that our... Okay, but here I want to say that if the morphism is finite, this is actually onto. This is a non-trivial, not entirely trivial thing. Okay, so assume x to y is finite. That is OY to OX, natural. OX is finite module over OY. Take X in X, X in X, or sorry, Y in Y, is represented by an ideal, by a maximal ideal. Any over. Clearly, MOX is not all of them. OX does not contain one, then there exists max ideal M prime in OX such that MOX is contained in M prime. Now M is inside. If you take now this M prime and intersect with OX, this is the pullback of M prime from X to Y.
Times O of Y, and prime times O of Y. That is
This should have been.
This is X.
Yeah, oh, thank you. I'm good. If you intersect with M of Y, then of course it contains the original M, and by maximality of M, this is